In the last lecture, we looked at the most important notion of vector spaces. Vector spaces are like the universe in which we carry out linear algebraic calculations. We found that the vector space is made up of two basic operations on a non-empty set V and a field F. The two basic operations are addition and scalar multiplication. We had the various laws connected with addition and scalar multiplication. Then we looked at a number of examples of vector spaces. Among them were these standard models and examples of f k, the collection of k by 1 vectors over a field F. In particular, if we take f equal to r, we get the real vectors, and if we take f equal to the complex number field, we get the C k. Then we had the model of the m by n matrices f m cross n, and in particular if we take the field to be the real field, we get the collection of all m by n matrices with real matrices which form a vector space, and analogously if we take f equal to C, we get the vector space of complex matrices. In particular, if we take m equal to n, we get the vector space of all square matrices of size n by n. Similarly, when we take f equal to r, we get the collection of all real square matrices. When we get f equal to C, we get the collection of all complex square matrices. The next collection of examples we saw were functions. So, we looked at a set S and we looked at a field F, and we looked at all functions from S to F, and we have the standard pointwise addition and pointwise scalar multiplication as the operations, and this was a vector space over F. In particular, if we take f equal to r, we get the collection of all real valued functions on S, which forms a vector space over R, and if we take the f equal to C, we get the collection of all complex valued functions over S, and this forms a vector space over the field C. In particular, if we take S to be an interval in R, then we looked at two special types of functions. One was L1 I R, which was the collection of all functions which belong to the collection of all functions from I to R, such that their integral over I of mod f t dt is well defined and is finite. And similarly, we looked at L 2 I r of all functions f from the interval I to C, such that the integral mod f t squared dt is finite. This should read R. We are looking at real valued functions. Similarly, in place of R, if we take C, we get complex valued functions in L1, complex valued functions forming L2. We shall now look at more examples of functions and their vector spaces. Again, we look at the collection of all functions which are defined on an interval and which take real values, and the C stands for continuous. So, it is all those functions which are in the collection of functions from I to R, such that f is continuous at every point in I. Now, with the usual addition laws for functions and scalar multiplication laws for functions, this is a vector space over R. Similarly, if we take the collection of all complex valued functions, they are functions from I, but they take complex values and f is continuous in I. Then this forms a vector space over C. We shall look at one or two more examples which are useful in analysis. Let us look at the next example, which we denote by f a lambda. This is the collection of all algebraic expressions of the form a naught plus a 1 lambda plus a k lambda k, and as we vary these coefficients over f and vary k over all non-negative integers. So, collection of all these expressions which we get by varying the a naught, a 1, a 2, a k's over f and varying k over the non-negative integers. Such expressions are called polynomials in lambda, and we add the polynomials as normal functions are added, and we multiply a polynomial by a scalar as normal functions are multiplied by a scalar. Then this f of lambda, the collection of all polynomials, forms a vector space over f, and the 0 vector in this vector space is the 0 polynomial. And if we have a polynomial, just like in functions, if we have a polynomial a naught plus a 1 lambda plus a k lambda power k, p is in f lambda, then the minus p is the polynomial defined as usual, which is minus a naught plus minus a 1 into lambda plus etcetera minus a k into lambda to the power k. In particular, if we take f equal to r, we get r lambda polynomials with the vector space of polynomials in lambda with real coefficients, and this is a vector space over R. The scalars have to be taken as R. And if we take f equal to c, these are two important fields which we will always be looking at, then we get c lambda, the vector space of polynomials over C. When we say polynomials over C, we mean the coefficients are C, and this is a vector space over C. The next example is a special version of polynomials. So, let d be any positive integer. For example, we can take d equal to 4 or 5 or whatever positive integer we need. So, let d be a positive integer and let f d denote polynomials first. So, they are all in f lambda, but they are special polynomials. Their degree of the polynomial p lambda must be less than or equal to d. So, you take the collection of all polynomials of degree below a certain threshold level, say d. Then this collection of all such polynomials form a vector space with the usual laws of addition and scalar multiplication over f. Again we repeat, if we take f equal to r, we get the polynomials, we will call simply, I will call it real polynomials, degree less than or equal to d, and we get c d. If we take f equal to c, the polynomials with complex coefficients will simply write complex polynomials with a degree less than or equal to d. We shall conclude our discussions of these examples with one more important example. We will be coming across many more examples little later. We will take one example from complex analysis and one example from Fourier transforms. Now, let U be the unit disk in the complex plane. What do we mean by the unit disk? U is the collection of all the complex numbers z such that mod z is less than 1. So, these are all complex numbers, which means you just take the unit circle in the complex plane and look at the interior. That is our unit disk. Take the circle of unit radius about the origin and look at the interior of that circle, and that is called the unit disk. Then by HU we shall look at all functions which are from u to c. These are functions from u to c, but we are not going to look at all functions from u to c. We are going to only look at functions from u to c such that f is analytic in u or holomorphic in u. F is analytic in u. Then since these are functions, we know how to add functions, we know how to multiply scalar and a function, and with these laws h of u, the sum of two analytic functions is an analytic function. If you multiply an analytic function by a complex constant, the result is again an analytic function. So, h u is a vector space over C. Now, we can replace u by some domain D in the complex plane C, and then we get H D, the collection of all analytic functions which are functions from D to C such that f is analytic in D. These vector spaces are very useful in complex analysis. One final example, as we said, on Fourier transforms. Let us look at L2RC. What do we mean? Recall, this means we are looking at all functions from R to C. That means they are defined for all values of the real number t. So, f of t, we have a function of t where t can vary from minus infinity to infinity over the real numbers, and the f of t, the value of the function at the point t, is a complex number. So, it is complex valued function of a real variable, and we are not going to look at all such functions. This L2 stands for those functions for which, if I take the mod f t squared dt, that is integrable. One has to be technical here, technically it has to be Lebesgue integrable, and that mod f t square which is Lebesgue integrable, the integral is well defined and the integral is less than infinity. This we will call as L2RC. Now, look at all these functions for any f in L2 or C, the Fourier transform, actually it should be called the Fourier Plancherel transform, is defined as, we denote the Fourier Plancherel transform by f hat. It is a function of omega defined as integral over r, which is integral between minus infinity to infinity, f of t e to the minus I omega t dt. Now, technically again we will not get into the details of the definition of the Fourier Plancherel transform. The integral has to be interpreted as an integral as a limit in the mean. Now, once we have this Fourier transform well defined, we look at a positive number omega. So, let omega be a positive real number, and look at b sub omega, which is all those functions in L2 or C. So, we are looking at not all the functions in L2 or C, we are looking at all those functions in L2 or C for which the Fourier transform is 0 for mod omega greater than or equal to omega. Here omega is again a real number. This function we take it as defined for all omega belonging to R. So, we are looking at all those functions in L2 R for which the Fourier transform is 0 beyond a certain stage. We say that the Fourier transform has support in the interval minus omega omega, that is f hat has support in the interval minus omega omega. Outside this it is 0. Such functions are called band limited functions. In the context of signal processing, these are called band limited signals with omega as the bandwidth. So, these are band limited signals or band limited functions with bandwidth omega. And since these are functions, we know how to add functions, we know how to multiply a function by a scalar, and we see that these form a vector space. B omega is a vector space over C. These class of functions, band limited functions, come in handy in signal processing and in Shannon's sampling theorem. Now, we have seen a number of examples of vector spaces. We shall be looking at more examples as we go on, but for the moment we shall have these examples in our bank and try to use them whenever we need. We now introduce another important concept, in fact the first important concept in vector spaces, known as linear combination. What do we mean by linear combination? Let us consider a field f. F is any field and V is a vector space over F. So, we have vector space over F. Let us look at a vector x in V. So, x is a vector in V. So, we have a vector in a fixed vector x in the vector space V, and now we see what are all the vectors what are all the vectors that we can build starting from x. Now, this question has to be explained further. What do we mean by build? You have to start from x, do something to it and then produce another vector. That is a vector which we say is built from x. Now, what can I do to x? The only two things that I know to do in a vector space are addition and scalar multiplication. So, build really means using the two operations in the vector space, namely addition and scalar multiplication. So, start with a vector x in V and see what are all the things that you can build using that x, and the thing that you are allowed to build are the only thing that you can do in that universe. In that universe of that vector space, the only things that we know to do are the addition and the scalar multiplication. These are the algebraic things that we have introduced and these are the only things that we can do. So, now let us look at addition. What can we do starting from x? We know only x, we can use only x. So, we can use x any number of times. So, you can use x and x. So, I will get 2x. So, 2x is a vector which I can build using x. Now, I can add x to 2x and I denote this with 3x, and so I can build 3x. Continuing this way, I will say for any positive integer n, we can build nx starting from x. So, that is the first building process. We shall now look at what we can do using scalar multiplication. Now, you see we already have one type of scalar multiplication generated by addition, namely nx. Now, instead of n, scalar multiplication says you could have chosen any alpha in the field. So, let us look at alpha in F, then we can build alpha x. As alpha varies over F, we get a large collection of vectors, and we see that this encompasses the nx which we have got already. So, addition can also be subsumed in this scalar multiplication. So, the conclusion is the vectors that we can build starting from x, again using only the vector space operations of addition and scalar multiplication, are precisely the scalar multiples. In fact, all the scalar multiples alpha x, alpha belong to f of x. So, starting from an x, all that we can build are the scalar multiples of x. So, that is one step where we start from a small thing and try to build as much information as possible. Then at the next level, let us start with two vectors x and y in V. Now, what are all the vectors? That we can build using x and y. Once again I repeat, when I say build, the only two operations, the only thing that you can do with these vectors are either add or do scalar multiplication. Now, let us look at the answer to this question. Starting from x, we have already seen that we can build alpha x, where alpha varies over f. Similarly, starting from y, we can build, say not alpha x, we use some other notation beta y, where beta can vary in f. Now, once we have these alpha x and the beta y's, we can add them, and then from this we can build alpha x plus beta y, where alpha and beta belong to f. So, thus we see starting from two vectors x and y. So, the conclusion is that starting from x and y in V, starting with two vectors x and y in V, we can build all vectors of the form alpha x plus beta y, where alpha belongs to f, beta belongs to f. Now, we extend this idea, we see that if we have in general instead of 1 or 2, if we have a finite number of vectors. So, let S be u1, u2, ur be a finite set of vectors in the vector space V. Then what are all the vectors that we can build using u1, u2, ur? Obviously, you can build alpha 1 u1 from u1, alpha 2 u2 from u2. So, u1 builds alpha 1 u1, u2 builds alpha 2 u2, and so on, ur builds alpha r ur. So, now these together build alpha 1 u1 plus alpha 2 u2 plus alpha r ur. So, the collection of all the vectors that we can build starting from u1, u2, ur, the vectors that we can build using the vector space operations are precisely those vectors which are of the form alpha 1 u1 plus alpha 2 u2 plus alpha r ur. So, starting, the conclusion of all our discussion so far is that starting from a finite set of vectors S equal to u1, u2, ur, where r is of course a positive integer, the set of all vectors that we can build using the vectors in S, or we will call them S vectors, using the vectors in S are precisely those vectors which are of the form alpha 1 u1 plus alpha 2 u2 plus etcetera alpha r ur, where the alpha j's are all in F. So, we have a large collection of vectors which we can build starting from these S vectors. Now, we give a name for all these vectors or the type of vectors that we can build from u1, and that is what is known as the linear combination of the vectors. So, we have a definition. Let S equal to u1, u2, ur be a finite set of vectors in B. Of course, we now have our always a universe as V vector space over a field F. This will be our universe. All the work will be done in a vector space V over a field F. So, let us take a finite set of vectors u1, u2, ur in a vector space V. Any vector of the form alpha 1 u1 plus alpha 2 u2 plus etcetera alpha r ur, where alpha 1, alpha 2, alpha r belong to F, is called a linear combination. It is actually, in engineering terms, it is a superposition of the S vectors, a linear combination of the vectors in S. From now on, for linear combination, we will just write LC as the short form. Now, let us look at some simple examples. Let us take the first example. Let us take the vector space V to be R3, and let us take S to be a finite set, say just two vectors, where u1 is the vector 1 minus 1 2 and u2 is the vector 1 0 1. Now, let us look at the vector u equal to 1 minus 2 3. U is a linear combination of vectors in S. We claim this. In order to claim this, we must show that u can be written as a linear combination of u1 and u2, which means we must find scalars alpha 1 and alpha 2 such that u can be written as alpha 1 u1 plus alpha 2 u2. So, we will simplify. It is easy to see, not very difficult to check, that u is equal to 2 times u1 plus minus 1 times u2. We see, for example, 2 times u1 plus minus 1 times u2 gives us 2 minus 1, which is 1, minus 2 0, which is minus 2, and 2 into 2 is 4, minus 1 is 3. So, therefore, it is easy to see that u is equal to 2 u1 plus minus 1. So, in this case alpha 1 is 2 and alpha 2 is minus 1, and both are in R. See, remember, our vector space is R3 and we must find the scalars in the vector in the field F, that is R, and that is what we have found. We have found alpha 1 and alpha 2 both real numbers. So, that is our first example. Let us look at our next example. Let us take the vector space to be the complex vector space now C3, and obviously of course our field is in this case is C. So, we will look at C3 as a vector space over C, and now again we look at a set S which consists of just say finite set. So, let us start again, look at two vectors u1 and u2, where u1 is 1 0 I. Now, the components can be, the entries can be complex because we are working over a complex vector space, and u2 is 0 I 1. So, we have a finite set of vectors u1 and u2, where u1 and u2 are as defined. Now, look at the vector u, which is 0 I I. This is again a vector in C3 because we are allowed to have complex vectors. We claim u is a linear combination of vectors in S. For this, we have to find two scalars alpha 1 and alpha 2. Now, the scalars are allowed to be complex numbers. So, we have to find two complex numbers alpha 1 and alpha 2 such that alpha 1 u 1 plus alpha 2 u 2 is equal to u. Again, it is easy to check that, I am sorry, let me make a slight correction here. This should be I and this should be 0. It is much easier, the calculations become easier. So, we have u is equal to I into u 1 plus u 2 or 1 into u 2. To be more precise, I into u 1 plus 1 into u 2. Let us check this. I into u 1 will give you I plus 0. So, that is I into u 2 will give 0 here, 1 into u 2 will give I. So, that is this I into u 1 will give minus 1 here, and if we add u 2, minus 1 plus 1 will give you this 0. So, u is equal to I u 1 plus I u 2. So, alpha 1 in this case is I, alpha 2 is 1, both are in C. Therefore, u is a linear combination of vectors in S. Let us look at another example. Let us take the vector space V to be the vector space of all 2 by 3 matrices. Again, we look at a finite set of vectors to make things easy, simple. Let us look at two vectors. Now, vectors are all matrices. Let us look at two vectors in this, where A1 is the matrix 1 minus 1 1 0 1 1 and A2 is the matrix 1 1 1 0 1 0. Then the matrix A, which is a vector in V, which is 1 minus 3 1 0 1 2, is a linear combination of vectors in S, since again it is easy to check that A is equal to 2 times A1 plus minus 1 times A2. So, in this case alpha 1 is 2, alpha 2 is minus 1, and therefore, we have expressed A as a linear combination of the vectors in S. One final example. Let us look at the vector space V to be the vector space of polynomials in the variable lambda. Let us look at a finite set. We should have vectors in V, but vectors in V are polynomials. So, we will say P 1, P 2, P 3. Let us take a finite set of 3 vectors, that is 3 polynomials, where P 1 is the polynomial P 1 lambda equal to 1 plus lambda, P2 is the polynomial P2 lambda equal to 1 minus lambda, P3 is the polynomial P3 lambda equal to 3 plus lambda. Now, let us look at P lambda, which is 2 plus 4 lambda. This is again a polynomial, its coefficients are in R. So, therefore, this is a polynomial. So, let us take f to be R to be much simpler. So, we have a polynomial over the reals, we have 3 polynomials, we are now looking at a fourth polynomial 2 plus 4 lambda, and P lambda is a linear combination of vectors in S, that is those polynomials in S. Since again it is easy to check that P lambda is 3 P1 plus minus 1 into P2 plus P3. Again, see, for example, 3 P1 will give me 3 into 1 plus, that is 3, minus P1 will give me minus 1. So, 3 minus 1 will give me the 2, this 0 is not this is 0 times P3, this should be 0 times P3. So, this is not contributing anything. Then look at the lambda terms, 3 P1 gives me 3 lambda and minus 1 P2 gives me another minus of minus lambda plus lambda. So, that gives me the 4 lambda, and the third term has no contribution. So, in this case we have alpha 1 is 3, alpha 2 as minus 1, alpha 3 as 0. So, thus we have P lambda is a linear combination of the vectors in S. Note, we can also write P lambda, the above P lambda, namely this polynomial 2 plus 4 lambda, as P1 lambda plus minus 2 times P2 lambda plus 1 times P3 lambda. Therefore, we see that the same polynomial P lambda is not only a linear combination of P1, P2, P3, which can be written as this linear combination, it can also be written as this linear combination. So, we have now chosen beta 1 as 1, beta 2 as minus 2, beta 3 as 1. So, the same linear combination, it may be possible to express as 2 different or more than 1 different ways as a linear combination of the vectors. Let us pursue this idea a little bit. To begin with, let us start with a vector space again. This is our universe, V is a vector space over F. Now, let us start with a finite set of vectors u1, u2, ur, and then look at linear combinations. What are linear combinations? These are vectors of this form alpha r u. And where do I have to choose alpha 1, alpha 2, alpha r? I am allowed to choose alpha 1, alpha 2, alpha r in the field F. In particular, we can choose alpha 1 as 0, alpha 2 as 0 and so on alpha r as 0. Suppose I choose all the alphas to be 0, what do I get? I get the linear combination, we get the linear combination 0 u1 plus 0 u2 plus 0 ur, which is the vector theta b. Thus, we see that whatever set we start with, whatever finite state u1, u2, ur we start with in V, we can always get the 0 vector as a linear combination of these vectors. So, we can build the 0 vector from any finite set of vectors. So, and therefore, the 0 vector is not of much use in building processes, because it can be anyway obtained from other vectors. Now, this particular linear combination that we have written in which all the coefficients alpha 1, alpha 2, alpha are 0 is called the trivial linear combination. This linear combination is called the trivial linear combination. That what is the trivial linear combination? It is the linear combination in which all the coefficients are 0. So, therefore, a linear combination is said to be non-trivial linear combination if at least one of the coefficients is not 0. So, alpha 1 u 1 plus alpha r u r is called a non-trivial linear combination if at least one of the alpha j is not 0. So, now what we have observed is that given any finite set S in V, the trivial linear combination of vectors in S yields the 0 vector theta v, and therefore, we can always get the 0 vector in this form as a linear combination of any finite set of vectors. This raises the following question: is the trivial linear combination the only linear combination that will yield the 0 vector? Is the trivial linear combination the only linear combination that will yield the 0 vector theta v? Let us look at one or two simple examples before we look at answer this question. Let us take V equal to R 3, the vector space R 3 over F. Let us take S to be u 1, u 2, u 3, a finite set of 3 vectors where u 1 is 1 1 0, u 2 is 1 0 minus 1, u 3 is 0 1 minus 1. So, we have a set of 3 vectors in R 3. Now, we investigate the question: is the trivial linear combination the only linear combination that yields theta v? Theta v in this case is theta 3. Let us look at that. Let us look at any linear combination alpha 1 u 1 plus alpha 2 u 2 plus alpha 3 e 3. If it has to be, our aim is to find a linear combination which gives the 0 vector. Suppose I have a linear combination which yields the 0 vector. What does that say? That says alpha 1 into 1 1 0 plus alpha 2 into 1 0 minus 1 plus alpha 3 into 0 1 minus 1 is 0 0 0, which implies alpha 1 plus alpha 2. Comparing the first coefficients, comparing the second coefficients, we get alpha 1 plus alpha 3 equal to 0. Comparing the third coefficients on both sides, we get minus alpha 2 plus alpha 3. And the only thing that can satisfy all these 3 equations is alpha 1 equal to alpha 2 equal to alpha 3 equal to. So, the only linear combination of these 3 vectors that can yield the 0 vector is the trivial linear combination. Therefore, only trivial LC leads to theta v. Let us look at another example. Again let us take V equal to R3 itself, but now let us take S to be U1, U2, U3 again, but now let us take U1 to be 1, 0, 1, well, let us say 1, 1, 0 like before, and U2 to be 1, 0, minus 1, and U3 to be 3, 2, minus 1. Now, we observe 2 U1 plus 1 U2 plus minus 1 U3. If you look at this 2 U1, let us look at the first components. 2 U1 will give me 2 plus this 1 3 and this minus 3, that will be 0, and then second component 2 and minus 2, that will be 0, and similarly the third will be 0. So, this will be exactly the thing. Now, we have a linear combination in which the coefficients are not 0. So, alpha 1 is 2 not equal to 0, alpha 2 equal to 1 not equal to 0, alpha 3 equal to minus 1. So, we needed at least one coefficient not 0, in fact, we have got many coefficients not 0. So, this is a non-trivial linear combination yielding theta b. So, now we have two examples, in one of which only trivial linear combination yields 0 vector, in another example in which non-trivial linear combinations that yield the 0 vector. So, there are sets for which only trivial will give 0 vector, and there are sets for which non-trivial linear combinations will also give 0 vector. We have to distinguish these two types of sets, and therefore, we give the following definition. So, let S be a finite set of vectors in V. We say S is a linearly independent set of vectors, linearly independent set. From now on, we will simply write Li for linearly independent set. So, from now on Li means linearly independent. So, we say S is a linearly independent set if the trivial linear combination is the only one that will give 0 vector. What does that mean? Alpha 1 U1 plus alpha r U r, where S is that set, let us say S is the set U1, U2, U r, then we say it is linearly independent, only trivial must give 0 vector. That means, if it is equal to 0 vector, this must imply all the coefficients must be equal to alpha, nothing else can give us the 0 vector. That is, only trivial linear combination of vectors in S can yield the 0 vector. If a set S is not linearly independent, we say it is linearly dependent. We write LD for linear dependent. We say it is linearly dependent. Notice, linearly dependent means, S is linearly dependent means that it is not linearly independent. Linearly independent means only trivial will give 0 vector. Not linearly independent means non-trivial will also give 0 vector, means there exists alpha 1 alpha r, at least one of which is not 0, such that alpha 1 u 1 plus alpha r u r equal to theta b. Now, this notion of linearly independent is a very important notion, and linearly dependent is the negation of linear independence. The fact that it linearly independence in some sense means the vectors contain redundant information, whereas when we say linear dependence means the vectors contain a lot of redundant information. Now, when we want to keep matter in a compact information in a compact manner, we would like to remove all redundancy. So, we would like to keep only linearly independent information. So, this notion of linear independence is a very important information. We will look at some examples of linear independence and see how it helps in building up process in vector spaces.